So this is just a recording to talk you through how a Shear box test is usually carried out. So these are the components of the Shear box itself. So there generally is the bottom and upper parts of the Shear box apparatus. There are numerous different plates. That's the base steel plate that usually goes in the bottom. And then you'll see small plastic plates, those white plates. They're used to grip the sample that is in the Shear box. The kind of pyramid-shaped one, that is the loading cap. So you'll see that's placed on the sample at the end. And then the load cell pretty much is connected to the top of that. Gareth is just placing screws in to connect the upper and lower parts of the Shear box. You can now see the plates going in. And those plates are going to go perpendicular to the direction of travel. So Gareth is just going to place in a sand sample. It's only a loose sample. Again, if this were to be carried out on clay, then a sample that would be at a certain moisture content, certain density, would be basically placed into that Shear box. The sample size is 60 millimeters by 60 millimeters square. Tends to be around 20 millimeters deep. So Gareth's just going to give it a tiny bit of compaction just to level off the upper surface of the sand. And when he's happy that that's finished, what he does is he puts the top plate in, and again that's going to grip the sample during the test, and then the load cap goes on. So that can now be placed inside the Shear box apparatus. So this is a Shearmatic Shear box. It is quite an advanced piece of equipment. In our lab there are two older versions of the Shear box as well. They all work on the same principle. So you can see the sample is being placed in to the Shear box. So this Shearmatic, instead of using disc loads to apply a normal load, you'll see in a few minutes the machine has some motors that actually can apply the normal load for you. So the camera may get a little bit shaky at times. Apologise. Cameraman is a fan of Blair Witch. So you'll see this is what the menu looks like. And what we'll want to do is obviously run a test. If you ever need to carry out Shear box tests, for example in a Year 3 project, then you'll be given full training. So what we're going to do with this sample is we're going to apply a normal load of 400 kPa, and you'll see on the screen there is various values of pressure. So the top one is going from 0 to 25, and basically on the right hand column you'll see EM, and you'll see most of them are yes, but there is one that's no. Where it says no, that means that's where the pressure is going to stop, and we want it to go to 400, so we change that to yes. And now you'll see the first no occurs at 400, 400 in the first and second columns. That means that the sample will be pressurized to 400 kPa and will just remain at that value. And it tends to apply that load in increments. Although it says consolidation, it is not consolidation that you're carrying out with this dry sample. So it is a sand sample. Consolidation would suggest that water is being removed, which is not happening. It's just a normal load. So now what we do is we set up certain specifications for the test. The standard speed is 0.4 millimeters per minute. The horizontal displacement of the sample, 6 millimeters. Maximum load, 5,000 newtons. And the area of the sample is 3,600 millimeters square, because the sample is 60 millimeters by 60 millimeters. So the test is almost ready to start. We haven't started it yet. So what Gareth is doing is he's now placing this kind of load arm on top of the sample. So this is going to connect up to the top of the load cap. And eventually the machinery is going to start pulling down on those arms, and that is going to apply a normal load to the sample to a value of 400 kPa. Slightly different with the older versions, where now you would have disc loads being applied to a very similar looking arm, but basically at the very bottom of those arms would be a plate where you can place disc loads to a value again of 400 kPa. So he's making sure everything is in contact. There's a little bit of movement there, and again what you need to do is remove any possible movement in the sample before you actually start the test. So at the end of the Shear-matic there's a little dial, a black dial, and that slowly moves the sample over and back, and basically it removes any initial movement out of the sample. So again, a little bit shaky, but you get the idea of what's happening. So what he's doing in here is very important. He's removing the screws that have connected the upper and lower parts of the shear box. He's just putting them, you could put them to one side, he's putting them into the other two holes. But they do not allow the screws to travel down to the bottom layer of the shear box. Very important that you carry out this step, otherwise as the shear box is moving, basically the lower half is going to remain stationary and the upper half is going to move. If those screws are in, you're not going to be shearing the sand, you're actually going to be shearing the screws. And you'll cause huge amounts of damage to the machine. So this is an LVDT. So this is there to measure any vertical movement of the sample. It's just a digital dial gauge. So during the test we're going to measure force, we're going to measure horizontal and vertical displacement. The pressure can be monitored. You'll see on the screen pressure has also been monitored, but that should be more or less stationary at a value of 400 as the test is ongoing. So I believe what Gareth is probably about to do, well, for example, you can see, for example, there the 4 different readings: load cell, pressure, horizontal displacement, and vertical displacement. And what Gareth is going to do, he's going to zero each of those to begin with. We're going to assume that there's 0 force, 0 pressure, and 0 displacement in both directions. It's just good practice to do that. Again, this is a little bit difficult probably to follow on the video, but what he's trying to do now is to get the PC that's set up to communicate with the shear box apparatus that we have. So it's something called hyperterminal that we'll use, and this basically gets both of them talking to each other. Just going to click transfer, just so we can start capturing data from the instrument, and he's just going to give it a file, a code of test 1. So now, about to start the consolidation phase, test is running, and you can see the pressure, for example, has now dropped, or has gone up to around 25. It's aiming at 25, but it's at 23 at the moment, so it does it in small increments. So the consolidation phase, what the machine calls a consolidation phase, is now underway. Remember, it's not consolidation, it's just a normal load. And now you can see we've reached the value that we want, we've reached a pressure of 400 kPa. So the test is paused, we haven't started the shear phase of the test yet. You can see there's been some movement vertically of the sample. So he's re-zeroed those, I think. And now you can see the test is underway, and you'll see the load cell is now recording pressure as the sample is being sheared. So that test will go until there is 6 millimeters of horizontal movement of the sample, and you can see the speed is being maintained at 0.4 millimeters per minute. So difficult to see there, but the upper and lower parts are actually, well, lower part is staying as it is, and the upper part of the shear box is moving at a very, very small rate. So eventually the test is completed, and we've got our measurements now of force, we've got our measurements of horizontal and vertical displacement. Again, a little bit difficult to follow, but now is the process of trying to capture that information from the shear box so we can actually use the software that we have to generate data and generate the graphs that we need. So again, don't worry, full training will be given to you if you need to do this. So the machine that we use is made by a company called Farrants, which make a large amount of soil mechanics testing equipment. So you'll see in a minute the software that we use is also provided by Farrants. So basically they have an Excel spreadsheet that's set up on the computer that we use, and that eventually will have all the data that we've generated during the test, and it will be exported to this Excel file. And the good thing about that is it will generate the graphs that we need as well. So to begin with, there's very little on this Excel spreadsheet apart from the size of the sample. You can see 60 by 60. And what we can do is we can load the data that we've just got from that test. So Gareth is going to go off and find the file. I think he actually uses, instead of the test one that we used, I think he uses, as you'll see, a different file, just because it was a test carried out in proper test conditions, and you'll see the data that was generated. Generally, you would find the same file again. So I think he uses a student file from a couple of years ago from GEL200. And we load the data, and we pick our units that we want to work in. And now you see all the information that we had is loaded onto this Excel spreadsheet, and our graphs are there as well. So we have our data in terms of displacement. We have our vertical displacement versus time graphs. We have our horizontal movement as well. So we've got our horizontal values against shear stress, which is calculated for us. So pretty much all the graphs that we need are generated on this. In a shear box test, quite often what you're trying to do is calculate the angle of friction. So you need to carry out 2 or 3 tests, and basically the peak or the residual values form points. And you'll see this graph down here, there's a single point because we only have one test result. But if we ran other tests at different normal stresses, we would have multiple points on that line, and from that we could get our angle of friction. Final couple of steps is just to complete the test, remove the sample, reduce the pressure. There's a little tap symbol on the Shearmatic instrument, and that now removes the pressure that's on the sample. Otherwise we cannot get the sample out of the instrument. So you can see pressure dropped off. And now the little home symbol recovers the sample. So basically the upper half of the box is now moved back into its original position, so that the total shear box mold basically can be removed with the sample as well. So that's pretty much how you would carry out a shear box test. It varies a little bit for each and every different type of apparatus that you can use, but that is the general steps. So now what I will do is send on each group sets of results that you can use to do the calculations to calculate, for example, angle of friction, look at latency, and so on.